Okay, so we'll start, Anup.
Yes.
Okay, so welcome everyone. Today we have Anup Dixit, and he will speak on families of L functions. Go ahead, Anup.
Thank you very much. Thank you, Krishna. It's always a pleasure to speak in CMI. So today I'm going to talk about this topic, which I've been thinking about for a few years. So the theme is on families of L functions. So let me first start by telling you what an L function is, in case some graduate students are around. So there's no precise definition, and as Huxley puts it in a joking way, we know it when we see one. But here's the philosophy behind these L functions. So we start with some arithmetic or a geometric object, and we associate a series to this object, a series of the type summation an over n to the s. Now it is unclear and these coefficients a n arise from these underlying objects, and typically in form of an Euler product. Now, once we have this series, this is a function of s. We can look at it as s can be on complex numbers. So this is a complex function. And this type of a series, typically it converges only on a right half plane. So what we will try to do is we'll try to look at analytically continue it. We'll look at, we will see if we can meromorphically continue this function to the whole complex plane, except for some few poles or things like that. And suppose there is a meromorphic continuation, then very mysteriously, the value distribution of the resultant function in the region where the series wasn't convergent, the zero distribution of these functions captures important information about this underlying object that we began with. So that is the general philosophy of L functions. We start with an object, associated a function to it, do some work on this function, and the resultant thing helps us in gathering information about the object that we began with. So let me give you a typical example. A typical example of L function is the Riemann zeta function, which is defined as summation of 1 over n to the s, or this Euler product of 1 minus 1 over p to the s inverse. And this series or this product is absolutely convergent on the region real part of s greater than 1. Now, just going back to the point earlier, the zeta function is associated, the underlying object here is just integers or natural numbers. Okay, so this is absolutely convergent for real part of s greater than 1, and this can be analytically continued through the whole complex plane except for a simple pole at s is equals to 1 with residue 1. And furthermore, after we have that this function makes sense on the whole complex plane, it also enjoys a certain symmetry. If I multiply this particular gamma factor to the zeta function, and the resultant function has a symmetry about the half line. So it satisfies psi of s is equal to psi of 1 minus s. And the famous Riemann hypothesis claims that, in fact, all the zeros in this critical strip lie on the line or on the half line. So one thing to note here is that because of this Euler product, there are no zeros on the right half plane to the right of real part of s greater than 1. And by this functional equation, you can show that there are only there are very few trivial zeros. You can figure out where the zeros are for the real part of s less than 0. So the mysterious region is this region, real part of s between 0 and 1, and there all the zeros lie on half is what Riemann conjectured. And the point to note here is, as I told you, this Riemann zeta function is associated with the underlying object integers. And this zero distribution, for example, if you assume Riemann hypothesis, that kind of gives you information about the prime distribution in natural numbers. So somehow this some kind of functional data here, some data about the value distribution of this function, this complex function here, captures information about some arithmetic information on natural numbers. In fact, prime number theorem itself is a consequence of the fact that zeta function doesn't vanish on real part of s equals to 1, and it has a pole at s equals to 1. Okay, so that is basically what the philosophy behind an L function is. So the way this talk is going to be structured is as follows. We are going to talk about certain families of L function. I will introduce a family. I will try to talk about the structure of that family, and certain properties there, and discuss certain theorems there. And in the second part of the talk, I will talk about one very specific subfamily in that family, and see that how studying these families of L functions together, in fact, gives us some very interesting arithmetic results. That is going to be the way the talk is going to be structured. Okay, so in order to, so this is just one example of an L function. There are other L functions too, like the Dedekind zeta function, which are associated to number fields, finite extensions of Q, Dirichlet L functions associated to characters, modulo Q, and so on. So now to put all these L functions under one single umbrella, Selberg introduced a class of L function, namely the Selberg class, and that is defined as all the meromorphic functions which satisfies the following properties. These properties are going to look very, very similar to the properties of the Riemann zeta function that we just described. So, so the function should have a Dirichlet series where the leading coefficient is 1, and it should be absolutely convergent on real part of s greater than 1. Should have an analytic continuation except for a possible pole at s is equals to 1. And there should be an Euler product of this type with some constraints on the coefficients of these Euler factors, slightly similar to that of the Riemann zeta function. And we also need certain symmetry. There should be a functional equation. That means if we multiply the function with some gamma factor, some factor of this type, then the resultant function should satisfy certain symmetric relation like this. And finally, we have a Ramanujan hypothesis, which is a condition on how fast the coefficients can grow, the Dirichlet coefficients can grow. Okay, so one point to remember here is that this functional equation is not unique because gamma function has the duplication formula. However, you can define some invariants using this functional equation, and namely the degree and the conductor. So the functional equation is not unique, but these are well defined. So the degree is defined as just twice of all these alpha i's, sum of all these alpha i's, and conductor is defined as in the following. And it's quite a folklore and important conjecture which says that this degree and the conductor are always non-negative integers. We will come back and hit this point in the course of this talk. Now let me give you some examples of elements in the Selberg class. Mostly all the interesting functions, that L functions that one can think of, lie in the Selberg class. The Riemann zeta function lies in the Selberg class. The Dirichlet L functions, Ls chi, or vertical shifts of these Dirichlet functions, chi the primitive character, are elements in the Selberg class.
That conjecture is supposed to follow purely from the theory of holomorphic functions. I mean,
sorry, this conjecture?
Yeah, because I mean, there is
that is one expectation, yes. But the thing is, so far we don't know anything about it. We only know what happens between 0 to 2.
No, but in Selberg class, there is, I mean, there is no arithmetic input at all, right? I mean, these are just
right. That is, so the thing is, I think there are two steps here. First, you show that these are non-negative integers, then you try to classify all elements there. Basically, in Selberg class, we expect that this class is exactly the same as all automorphic L functions, all L functions coming from some nice automorphic forms. That's, this is, I think, the first step towards it. First,
okay. Even though a priori, I mean, there is no arithmetic going into the definition, right?
Yet, yes, that is correct. Yeah, that's right. Mm-hmm.
Okay, thank you.
Yeah, no problem. Okay, so giving certain examples and just making sure that all the familiar L functions are there. So we have this Dirichlet L functions, Dedekind zeta functions coming from number fields. This is the definition, summing over norms of all the integral ideals to the power s. And Artin L functions are also in the Selberg class, assuming the Artin's holomorphic conjecture, which claims that Artin L functions are entire. And if you look at modular forms, if you have a holomorphic new form of weight k, suppose this is its Fourier series, then you normalize the Fourier coefficient in this way, just so that the pole is at 1. And then the resultant L function is also in the Selberg class. Now, it doesn't necessarily have to be a holomorphic new form. For non-holomorphic new form, we expect it to be in the Selberg class, but we don't know the Ramanujan hypothesis for them. And then if you have any two holomorphic new forms, look at its Rankin-Selberg convolution, and the L function attached to the Rankin-Selberg convolution should also be in the Selberg class. So mostly all interesting L functions seem to be in this particular class. But of course, it misses out on a few things, like it doesn't contain linear combinations of L functions, for example. It doesn't contain Hurwitz zeta functions. Hurwitz zeta functions with rational parameters can be written as a linear combination of known L functions, but those things are not present in this class. So there are certain limitations. So let's try to first get rid of those limitations. So we introduce this class M. So first thing to note is if you have f and g in the Selberg class, then its product is in the Selberg class, forms a semi-ring, but its sum is not in the Selberg class. So one of the main goals would be to define a larger class of function which is based on growth conditions rather than functional equation and Euler product, and such that it forms a ring. And then we introduce an invariant purely based on growth conditions, which would mimic the degree in the Selberg class. And then we study its algebraic structure. Now that we have addition and multiplication, it will have some more structure to it. And we can study the value distribution, which is basically, if it is coming from some nice underlying object, the value distribution would have some meaning. And then hope we will hope that there is some more geometric structure to it, and that's going to be that is what I'm going to do for the first half of our talk. Okay, so let's look at let's try to introduce this class. So first, let me introduce certain growth parameters. So instead of going through it line by line, what's happening here is for a function, for a given function with Dirichlet, which has a Dirichlet series and an analytic continuation, for a given sigma, I want to see how it is growing on the vertical line. A real part of S is equals to sigma. So the first parameter captures exactly the growth of it on the entire on that entire line. And the second parameter captures what happens eventually. It doesn't really care what happens what happens to the function, how fast, how large it is near the real axis. It just cares about it, what happens eventually to this function. So these are two growth parameters. And now we introduce a new class. Okay, so this is what I just mentioned. Now we introduce this new class M, which has the following properties. It has a Dirichlet series. It has an analytic continuation, except for a possible pole at S is equals to 1. And here we also enforce the condition that it has to have a complex root order 1, because in the previous case in the Selberg class we already got this complex root order 1 because of functional equation, but here we have to enforce that. And then we have this growth condition that this mu f of sigma that we just defined divided by 1 minus 2 sigma is bounded. Now there is a reason for that, because we want to extract the information that is captured by degree of the functional equation using growth conditions. So that's why we look at this kind of quantity to be bounded when sigma is less than 0. And we also enforce Ramanujan hypothesis, which is just a bound on the coefficients of the Dirichlet series. Okay, so so now we define these two invariants, CF and CF star. So these are invariants which would mimic the notion of degree. So it is defined as lim sup of sigma less than 0 of this quantity, twice of mu of sigma over 1 minus 2 sigma, and twice of mu of star sigma over 1 minus 2 sigma. Now, because of the growth condition, both these things are well defined. And it is also easy to see that CF star is less than or equals to CF, because as we saw earlier, mu F star did not care how F behaves close to the real axis. And in case of the Selberg class, if you have a functional equation, then all these things are the same. CF and CF star are the same, and they are also equal to the degree, df. Okay. Now let's look at some examples in this class. So if you look at a Dirichlet polynomial, which then that is an element in this class. If you look at the Dirichlet series, which is absolutely convergent everywhere, for example, summation e to the minus n over n to the s, which is convergent everywhere, that is also an element in this class, and that has CF star equals to 0. And as we will see in a later theorem, that these are precisely all the elements with CF star equals to 0. And then, of course, the Riemann zeta function is in this class. The Selberg class is in this class, and CF and C zeta and C zeta star will be 1 because the degree is 1 for the Riemann zeta function. And if F is in the Selberg class, then F is also in this M. And furthermore, translates of F are in M, and if you look at FRS, then that is also in M. And in these two cases, again, the CF and the C of the translates will be the same as CF, and C of FRS will also be the same as CF. Okay. So interestingly, these invariants satisfy this ultrametric condition. So this comes purely from the definition and using Krag-Van law and some basic analytic number theory. You get that this basic complex analysis, you get that these satisfy these ultrametric conditions, and that curiously helps us in okay. First thing to note is, because it satisfies the ultrametric condition, one can show that M is closed under addition as well, and therefore M forms a ring. So we have a ring now, and furthermore, because it has this ultrametric condition, it is natural that this will give rise to a metric on the space M. There will be a notion of distance. So you can talk about the topology of M. You can talk about completing M and looking at the limit points, and this will be a relevant thing when towards the end of the talk. Okay, so now we have a ring of L functions. And let's look at, okay, first let's look at how the CF and CF star compare with that of the degree. So as the question was raised by Professor Ramdas, that in the degree conjecture, it didn't seem like we were using any underlying structure at all. It just seemed like a question on the function itself, just a complex analysis question rather than something that had to do with some underlying object. That seems to be in our new definition. We have completely forgotten the functional equation and the Euler product. So that seems to be the case, but it has its own limitations. So here's what we have. So first off, for the degree in the Selberg class, we know the following. So it was a result due to Conray and Ghosh, and they showed that if degree cannot take values between 0 and 1, if it is between 0 and 1, it has to be 0 or 1. And much later, with a lot of work, it was shown that degree cannot take values between 1 and 2. And this is the result due to Perelli and Krag-Zarowski. So, and in fact, we know the complete classification of all the elements in the Selberg class with degree equals to 1. No such classification is known for higher degrees. Like, we don't know what are all the L functions with degree equals to 2 in the Selberg class. So if one wants to raise the same questions in our case for the class M, then we have the following. So this is joint work with Kumar Murthy. So we say that if you have an element in M, then the CF star cannot take values between 0 and 1. So this becomes significantly harder to show when you are just working with degree, but nevertheless this is true. And this follows from certain works of Landau. And in fact, we are also able to classify all the elements with CF star equals to 0. And that is precisely given by all these Dirichlet series, all the entire Dirichlet series, which are convergent everywhere, up to a Dirichlet polynomial. Okay, so that's the classification of the classification problem in this context. Another problem that one can look at okay. So first, let me discuss certain algebraic structures of this algebraic properties of this ring M. So it's a non-Noetherian ring, and hence it's non-Artinian. Now, usually, when you prove something is non-Noetherian, that's a bad thing. But in this case, it actually gives us a little hope about something else. So in the Selberg class, there is this notion of primitive elements. So you have you look at so those elements which cannot be further factorized are called primitive elements. And it's a conjecture that every element can be uniquely factorized into primitive elements in the Selberg class. That's the consequence of Selberg's orthonormality conjecture. Now, what we know is that if the Selberg's unique factorization conjecture is true, then the group ring over complex numbers of the Selberg class is in fact non-Noetherian. And this M is not, doesn't a priori doesn't seem very far from this group ring. M contains this group ring, and it is unclear at this point, but it is possible that it's just a finite containment. If that is the case, then we would have that CS is non-Noetherian. This is again this is something which is not known. So this makes this observation or this property interesting. That your M is non-Noetherian, and also we have that if F is in M, then its derivative is also closed under derivatives, which is another interesting property just to throw in there. Okay. So now I'll move to one specific type of problems on this class M, which has to do with value distribution of elements in M. Now, there are several angles in which you could pursue the investigation. I'm only going to talk about one particular type of problem, and then later on we will go to the second part of the talk. Okay. So let me talk about the A values of a function. Now, for a meromorphic function, A values are where the set where the function takes value A. Now, there are two ways of looking at this set. One is I can look at it as a multi-set, like if f of x minus a has a double zero, I count it twice. So I can look at it as a multi-set, or I can just look at it as a set, ignoring multiplicity. So there are two ways of looking at A values of a function, as multi-sets, which is counting multiplicity, as just as sets, ignoring multiplicity. Now, a question is that how many, so if you look at two distinct meromorphic functions, how many values can they share? Can it happen that two of them have exactly the same A values? And this was answered by the beautiful theory developed by Nevel, who showed the following. If you have two meromorphic functions, and let's say if they share 5 distinct values, ignoring multiplicity, just as sets, sets, you have 5 distinct values. Let's say 1, 2, 3, 4, 5. One value of f is same as one value of g, and two value of f is same as two value of g, and so on. Then f must be equal to g. But if you ignore multiplicity, and if they share 4 distinct values, then they are almost similar. F is in fact the Mobius transform of G. And this 4 and 5 are the best possible for meromorphic functions. So because we are in the context of L functions, our question would be, can we do something better if we replace meromorphic functions with L functions? So the answer to that should be yes, otherwise I wouldn't be mentioning it. But to demonstrate how powerful how restrictive this type of question becomes when we talk about L functions, let me give you one very simple observation and simple proof. Let's say you take two distinct L functions in the Selberg class, and let's say they share one value counting multiplicity. So wherever L1 takes value A, L2 also takes value A with the same multiplicity. So can it happen? The answer is no. And this is a very simple argument to demonstrate that. Suppose for simplicity, assume that A is not equals to 1, and also assume that L1 and L2 are entire. If they're not entire, you can fix the poles by multiplying it with some suitable Dirichlet polynomials, but let's just assume that they're not entire. Now consider the function L1 minus A divided by L2 minus A. Now because they share A values counting multiplicity, this function is going to be an entire function, and it is going to have no zeros and no poles, because they share A values counting multiplicity. No zeros, no poles, so it has to be an e to the power of an fx. But this exponent has to be a linear function because your L1 and L2 have complex order 1. So it's exactly going to look like e to the cs plus d. But what I also know about these L functions in the Selberg class is that the leading coefficient is 1. So if I take my s to go to infinity on the real line, then I know that both L1 and L2 converge to 1. So I can look at L1 minus A over L2 minus A, then that converts to 1 minus A over 1 minus A. But for I had assumed that A is not equals to 1, so that should be 1. And therefore you get C is equals to D is equals to 0, and you get L1 is equals to L2. So just by the virtue of the being a Dirichlet series and having an analytic continuation, we can basically show that L1 and L2 cannot share one value counting multiplicity. So in this context, there have been several results, and these are sometimes called strong multiplicity theorems. So the first of this kind was proved by Rammurthy and Kumarmurthy, who showed that if L1 and L2 in the Selberg class share zeros except for certain error set, like except for a few zeros, they share almost all zeros, then in fact they must be the same. Now, if you ignore multiplicity, things become much harder, and this is rather deep results of John Studing and Bao Kin Lee, who showed that if L1 and L2 are in the Selberg class with the same functional equation, and if they share two values ignoring multiplicity, then they must be the same. The natural question is, can we prove similar theorems for M? And another aspect of the problem is, if you look at some random meromorphic function and an L function in M, how many values can they share? So towards this, we don't have this result for M, but we can prove it for something. We can prove it with some additional condition. So the additional condition that I will throw in is a strong growth condition. It is essentially saying that the growth that we are expecting is attained at a shorter height from the real axis. That's basically what this growth condition is capturing. And if you assume this, then you can show that first you can show that the number of A values is of the right order what you expect. And then you show that if L1 and L2 share one complex value, then they are almost similar. And if you have some meromorphic function and an L function in M1, and suppose they share one complex value counting multiplicity and another one ignoring multiplicity, then in fact they are the same. In fact, you can further relax the condition that they ignoring multiplicity up to some big error term. So what you have is some random meromorphic function and an L function, and they share one value counting multiplicity and another value ignoring multiplicity. They are the same. So all these theorems involve, the proofs of all these theorems involve some very nice applications of Nevalnina theory. And because we also observed that your M is closed under differentiation, so we can throw that in and also get some uniqueness results in that context. If you have a meromorphic function such that and a L function such that they share one value counting multiplicities and their derivative shared zeros up to some error term, then they are almost the same. One is a constant times the other. So these are types of value distribution. This is just one aspect or one style of the value distribution results that one can obtain over this class M. Okay, are there any questions so far? All right. Okay, so the next, and there are several other lines of investigation. Like one can look at what are called universality type results, and those will also be valid. Some of them will be valid, some of them will become more complicated for this class. But this is the only aspect of value distribution theory that I wanted to speak about. So now we will go to the next part of the talk, where I would restrict myself to one particular family of L functions. Namely the Dedekind zeta functions, and I will try to retrieve some interesting information about the underlying fields. So let's see the problem that we are looking at. The problem that we will be considering will be the class number problem, which is a more common and fashionable problem to look at. So suppose K over Q is a number field. That's a finite extension of Q. We define the class number as the order of the ideal class group, which is basically look at the fractional ideals quotiented with the principal ideals. So class number kind of captures how far the ring of integers of this field is from being a PID. For instance, if you look at rational numbers, then the ring of integers is just integers, which is a PID. So we have class number is 1. Again, Gaussian integers are a PID. So class number of Qi is 1. However, Q root minus 5 is not a PID, and their class number is in fact 2. So classical problem in number theory is to understand how this class number varies on varying number fields. So in that context, this problem begins with conjectures of Gauss, who in fact conjectured that for imaginary quadratic fields, fields of the type Q root minus D, he said that there are exactly 9 imaginary quadratic fields with class number 1. And this problem was fairly recently was resolved in mid 20th century independently by Heegner, Baker, and Stark. Furthermore, he also conjectured that if we vary over imaginary quadratic fields, then the class number must go to infinity. That means if you give me a bounded class number, there are only finitely many imaginary quadratic fields of that type. But this was resolved by Heilbronn, using the famous Davenport-Heilbronn phenomena, where you have that if the Riemann hypothesis is true, you get a theorem. If the Riemann hypothesis is false, you also get the theorem. It's a very interesting pieces of mathematics. And then he also conjectured that there are infinitely many real quadratic fields with class number 1, and this is still open. In fact, to all the graduate students out there, Peter Sarnak has mentioned that if anyone can crack this, he will give him his position at Princeton University. Okay, so this is where the story began. And this is the question that we are looking at. How does the class number vary on varying number fields? So this seems like a very arithmetic problem, but the only approach to this type of problem so far is through the study of L functions. So here's what we will do. So first off, this question is very difficult. So we will make it slightly easier. And instead of looking at how class number varies on varying number field, we will look at how class number times the regulator varies on varying number fields. And this regulator is an invariant which captures how dense or how sparsely units are in the ring of integers. So if the regulator is small, that means there are way too many units. And if regulator is large, then units are sparsely present in the ring of integers. Okay, the bridge between analytic and algebraic number theory is the class number formula, and that is what we are going to use in this context. Let's say, so first look at the Dedekind zeta function, something that we already looked at. It's defined as this Euler product. So product over all prime ideals in OK, 1 minus 1 over norm p to the s, its inverse, and this is absolutely convergent for real part of s greater than 1. Now, the Dedekind zeta function is an element in the Selbach class, and it has a simple pole at s is equals to 1. It has an analytic continuation and all the familiar properties that you require. It has a functional equation and so on. So the class number formula tells us the following. Suppose rho k is the residue at s is equals to 1 of the Dedekind zeta function, as I just said, it has a simple pole at s is equals to 1. So let's say rho k is the residue. Then there's the beautiful formula which relates the residue with all the known invariants of coming from the number field, like a class number, the regulator. Here dk is the absolute value of the discriminant, and omega k is the number of roots of unity in k. R1 is the number of real embeddings, and R2 is the number of complex embeddings of k. So this is the beautiful class number formula. And this is what we will use to approach the problem of how the class number times the regulator vary on varying number fields. So this is what is called the classical Brouwer-Siegel conjecture, and this was conjectured by for certain fields. This was proved by Siegel and Brouwer, and I will mention that in a second. So the conjecture says the following: suppose you have a family of number fields, and let's say the root discriminant goes to infinity as I goes to infinity. So that means the discriminant is growing much faster than the degree in this family of number fields. Then he says that the class number times the regulator also goes to infinity as I goes to infinity. In fact, it grows at this particular rate. The log of class number times the regulator divided by log root discriminant goes to 1, is equals to 1. That means log of class number times the regulator grows exactly at the same pace as log root discriminant. And we know that discriminant must go to infinity as I goes to infinity because of Minkowski bound. There are only finitely many number fields with a bounded discriminant. So this is what we achieve. But the way we achieve it is by translating this problem through the lens of class number formula to this particular problem. So this, if I use class number formula, remember that class number formula looked this way. So if I take log of rho k divided by log root discriminant, here we will have a log of class number times the regulator. And that is precisely why we can't separate out the class number and the regulator. Okay. So this is same as showing that log of the residue divided by log root discriminant goes to 0. And that will bring us down to studying families of this Dedekind zeta function, knowing how knowing some zero-free regions of them to get these kinds of estimates, and that will enable us to show these type of results, which are very arithmetic in nature. Okay, so Siegel proved this for quadratic fields. So this conjecture is known for quadratic fields, and Brouwer showed it for Galois fields. And moreover, he also showed that if you assume the generalized Riemann hypothesis, then you get it for all families of number fields as long as this root discriminant goes to infinity. Okay, so one of the things that we will do is we will try to relax this condition. This root discriminant goes to infinity. We will try to relax that condition and get some unconditional results, which were not known before, without assuming GRH, and then get some effective versions as to how fast is this going to 0. Or how fast is this going to 1? So that's what we will do right now. So in order to state this conjecture where we do not assume this root discriminant goes to infinity, we have to introduce what are called the notion of asymptotically exact families. Let me see how I'm doing on time. Okay, good. So we say that a family of number fields is an asymptotically exact family if these invariants are well defined over the families. So these invariants essentially capture the way primes split over this family of number fields. We don't want the splitting of primes to be too erratic. So like for example, if you look at a tower of number fields, that will always be asymptotically exact. So this basically nki of q is the number of primes, number of prime ideals in ki with norm q. And R1 is the number of real embeddings, R2 is the number of complex embeddings. So these are Archimedean the invariants in the Archimedean places. So once these invariants are well defined, then we say a family is asymptotically exact. So in the classical setting, when we had the root discriminant goes to infinity, that was precisely same as saying that each of these invariants is 0 for all q meaning for all prime powers q. And if that is not the case, then we say these are asymptotically good families. So this is the modern type of families. Now, this is the classical set of families, and this is the non-classical families. And such families do exist because if you look at a Hilbert-Glasville tower, there the root discriminant is a constant. And those types of towers or families don't fall under the classical Brouwer-Siegel conjecture. So we will need, so this in fact captures them. Okay. So this asymptotically exact families were introduced by Fasma and Vladuch, and they in fact so it's a very beautiful paper, and they talk about the generalized Brouwer-Siegel conjecture in this setting, and they make the following conjecture. They say that the ratio that we were after, log of class number times the regulator divided by log root discriminant, can be exactly written down in terms of these invariants that we just described. Now, in case of, just for sanity check, in case of the asymptotically bad family, the classical setting, all these things will disappear. All these things are 0. So this would be exactly equal to 1 as we had seen earlier. But otherwise, we have these, it can be described in terms of this invariant. And same with, and this, if you use class number formula, this exactly looks like the following. Log of the residue over log root discriminant would look like this. Okay. So we and now again studying these families of L functions, families of Dedekind zeta functions corresponding to these fields. I in fact showed that for asymptotically good tower and asymptotically bad families of number fields with solvable Galois closure, we get this conjecture. So earlier, this conjecture was known for Galois families, like where the family is asymptotically good or asymptotically bad family of a number of fields which are Galois or almost normal. So I showed it for some other families in this context. So this conjecture holds in these families. So so I must emphasize on the fact that these arguments are purely analytic in nature. There is absolutely no algebra used, although the final results are arithmetic. There is a very tiny bit of arithmetic or algebra used in these type of results. Okay, so furthermore, we get some effective versions too. Like for asymptotically bad family, that is in the classical setting, Stark's work shows that if you have a family of almost normal fields means so I should also said what solvable closure means. So almost normal field means the following. We say K is almost normal over Q if there is a tower going from Q to K such that at each level it is normal, it is Galois. And when I said solvable, so fields which have solvable Galois closure, I meant K is said to have solvable Galois closure. If I look at the Galois closure of K over Q, then I look at its Galois group, then that I want that group to be solvable. Those are called groups. Those are called fields with solvable Galois closure. For example, if you look at this family where you keep on adjoining, let's say Q adjoin with cube root of 2, then cube root of 3, cube root of 5, and so on, then that will give you a family of number fields, tower of a number field, where at each step you will have solvable Galois closure. So there are examples which were not known earlier, where we get the Brouwer-Siegel theorem. Okay, so Stark showed that the rate at which this log residue over log discriminant goes to 0 is at least of this order, log root decay divided by log decay. And I showed that this log of this for the solvable Galois closure case in the classical setting, this grows to 0 at least at this particular pace. Now in analytic number theory talk, if you don't have logs, then it is no longer an analytic number theory talk. So here you go. And then assuming GRH, you in fact get the following rate at which this quantity goes to 0. So now let me end by just bringing your attention back to what we started off with. We started off with this Lindelof class, and we introduced this new class M, and where we defined everything. And so let me just show certain connection to this of this particular problem to this Lindelof class setting. In fact, these objects that we were studying over asymptotically exact families, we wanted to show that we wanted to show certain like the certain way these log of the residue over log root discriminant behaves. So those have interpretations in terms of what are called limit zeta functions. Now, limit zeta functions are defined on families of number fields which are asymptotically exact, and they are defined in this way, where phi q's are the invariants we just defined. Now, these L functions, you wonder where they lie. So we don't, it's unclear a priori whether these functions have analytic continuation. In fact, it is conjectured that they can be, in fact, under the Riemann hypothesis, you can only analytically continue it up to half, real part of S greater than half. Otherwise, is a convergent on real part of S greater than 1. And many interesting properties about these number fields are captured in this. Like it is conjectured that the value at half is 0 and things like that. There are many interesting properties that are captured. But you wonder where this function lies. So this function, in fact, turns out that it is one of the boundary elements in M. It is not an element in M, but it can be well, if you use the topology in M, which is not like you can always say that this can be written as a limit of several Dedekind zeta functions, but that's not how it will work. If you use the topology that I did not describe of M, then these elements are in fact in the boundary elements, and it's an interesting question to investigate. What do these boundaries mean when we are looking at this space of L functions? And that's rather mysterious question, and there are several avenues of investigation there. Okay, I hope this gave some idea about families of L functions. I'll stop here. Thank you very much.
Thank you, Anu. Are there any questions? Okay, so if there are no questions, let's thank Anup for a very nice talk. Thank you, Anup.
Thank you.